Okay, thank you very much. First of all, thank you for the invitation. I'm sorry I cannot be there in person. I hope you're having a wonderful meeting. I really like this idea of connecting people from different areas, physics and philosophy, and discuss about quantum gravity. So thanks for the invitation. Okay, so I'm gonna explain you why. I mean, in the recent years, there is a lot of activity on the Swampland program, which is a new approach to connect quantum gravity to the real world, which is so needed in this time of quantum gravity without experiments. That is the title of the workshop. So I'm gonna start very basic, just to make sure we are all on the same page. And if at any moment you have any question, please don't hesitate to interrupt, okay? Even if I am not there in person, I'm happy if we can make the talk as dynamical as possible. Okay, so as I said, let's start from the beginning. So when doing research in physics, we aim to expand the knowledge, the frontiers of knowledge. And it's all a matter of scale. So we live some intermediate scales with our own eyes. We can probe and understand the physics around us. But in the history of physics, we have developed more sophisticated experiments to be able to probe the physics at smaller scales, smaller distances, which is equivalent to higher energies. You have to put more energy into the system to probe smaller distance, or to probe larger distances in cosmology. So particle physics studies the constituents of matter at very small scales, what happens at small distances, and cosmology studies the universe at very large distances. And this has led to the consolidation of the two standard models that we have in theoretical physics, in fundamental physics nowadays, which is the standard model of particle physics that provides a quantum description of all elementary particles and interactions except for gravity at small distances, and the standard model of cosmology, which is a classic, not quantum, description of gravity given by general relativity. So these were the two big revolutions of the last century, quantum mechanics and Einstein general relativity. And as all of you know, the big challenge now is to unify them, right? Like to unify gravity and quantum mechanics in a theory that can describe quantum gravity. So since quantum mechanics describes very small systems and general relativity describes very massive systems, quantum gravitational effects will become important at very small scales, very small distances, and very massive objects. So how can we probe this? I mean, if we want to directly test quantum gravitational effects, it seems we need to go to very extreme situations, like, for instance, the beginning of the universe, the Big Bang, in which we have a lot of mass in very small distance, or inside of the black holes, where we have also the singularity, we also have a lot of mass in a very small distance. And this is why it's hard to probe experimentally, right? Like quantum gravity, because we don't have the technology, to access these regimes. But still, it's amazing how much progress we can make just by requiring consistency, by trying to unify the both frameworks, okay? So can we construct a consistent theory of quantum gravity? Yes, we can. For example, the leading candidate is string theory, as we were discussing in the previous talk. And regardless of whether this is the full theory of quantum gravity that describes our universe, at least we know that this is a theory of quantum gravity. So we can use this as a thought laboratory to understand quantum gravity better. Now, you would say, okay, very good. So we are working on that. We are making progress. But now what? Like, can we test it experimentally? Can we connect it to the real world? Right? This is one of the big open questions. Or constructing a consistent theory of quantum gravity is just some theoretical exercise without implications for our universe. In other words, does quantum gravity matter at low energies? Or is this just a thoughtful experiment? Can we somehow predict some implications from quantum gravity for the physics that can be detected nowadays with the current experiments? So this is the question that, I don't know, like that I find more interesting, that really drives my work from the very beginning. And typically, so, well, let me try to give you what is the answer. So in order to answer this question, we need to understand how we typically describe physics, right? So what is called like the Wilsonian effective field theory approach, okay? So in the history of physics, it's been very useful to divide the problem in pieces, in the sense that you focus on some scale and focus on some energy scale or some distance, and then you construct an effective field theory, right, that describes the physical phenomena up to some energy cutoff. Okay? So it's valid up to some energy cutoff, and then in this region, I can describe what's going on. Like, for instance, I have fluid dynamics, or if I go to smaller distances, I realize that I have atoms, and then I have atomic physics. Then we see that they have some constituents, fundamental constituents. We have the standard model of particle physics with the quarks and the electrons and so on. And if we continue and so on, going to smaller distances or higher energies, we would expect, for instance, to get string theory. Okay, so this is very useful. This is how we have made progress in physics. And it's very important that when we have some description and we go to a higher energy, it's not that the theory was wrong, it's just that we need to complete it. Okay, so that's how things work in physics. We just complete the theories as we go to higher and higher energies. Now, I put here some scales. These are energy scales. We can also put distances in meters, but just to have an idea, this is what we have, the Planck scale. This is where the Higgs boson that was detected at the LHC lies, the electron, neutrinos, and so on. This is the regime which is accessible at LHC here at CERN. And quantum gravity is expected to become important at very high energies, right? Because, I mean, all of you know. So this is the Planck scale, 10 to the 19 GeV, or equivalently 10 to the minus 35 meters. Okay, so taking this into account, these scales, the difference of scales, since quantum gravity seems to be relevant at very tiny scales, it seems that it's not going to have an impact on the physics that we detect now at the LHC or at other experiments, right? Because it's like it's a completely different scale. And this is the traditional answer, okay? Like saying, okay, no, quantum gravity doesn't really matter, it's going to become irrelevant, and that's why it's so hard to detect and to predict. Now, the message of this talk is that this is actually false, okay? And that quantum gravity can have implications at low energies, even if the Planck scale is very high. So I will try to explain why this is the case and introduce what is the Swampland program. Okay, so let's just, for fun, try to make it simple first. So imagine the picture of a landscape, okay? Beautiful landscape. And then we start zooming in the landscape, okay? And at some point, we can see the fundamental pixels, okay? Like we notice that they are like different squares if we are close enough. Now, from the very far away from long distances, I don't have access to these pixels, but for instance, the rules to combine the different colors of the pixels can have implications for the landscape at large distances, right? Like this seems obvious. So just to make it a bit fun, you'll see later why I take this analogy. If I tell you that, for instance, we cannot have pink pixels, that means that they cannot have flamingos in the landscape, and that's a prediction that you can say. Or if I always have brown pixels in between blue and green, then maybe one can try to conclude that there are mountains in the background. Or if I have some symmetry, like there is some reflection, this is what in physics would say that, for instance, I have a discrete symmetry, which is C2, so the rank is smaller than 3. then you can argue that you have the sky and also some lake. So the point is that even if we cannot see the pictures, the rules matter, because if we don't satisfy these rules, maybe we end up with a swamp, okay, which is nothing to do with the landscape. So what I'm doing here is just saying that these pictures that we see at long distances are like different effective field theories, and we can have different zooming. We can see it at different scale. And these rules is what I will call these quantum gravity constraints. So when I was saying that we just describe the physics at different scales, it's just like zooming in this landscape. And then a very important message is that not everything goes. Like if you have some fundamental rules of what are the fundamental constituents, you cannot generate any possible landscape. So not every effective field theory that you construct is going to satisfy in general the rules of quantum gravity, even if the quantum gravitational effect only become important at high energies. And I'm using this stupid analogy, which maybe is a bit ridiculous, but I'm using it because this is precisely the names that we use in physics to distinguish between those theories that satisfy these quantum gravity constraints, which belong to the landscape, and those theories that do not satisfy these fundamental quantum gravity constraints and belong to the swampland. Okay. So it's more correct, instead of just this picture of a plane, it's actually the picture I like to put is more like a cone, because the space of effective field theories that we can have depends on the energy scale. And these constraints become more important as you go to higher energies, okay? But anyway, the point is that not every effective field theory, not every model that you construct to predict what's going to happen at the LHC or what are the new particles that are going to appear and so on, not all of them will be able to be completed in quantum gravity, okay? So not all of them can arise as low energy limits of quantum gravity. And those that cannot is what we call the swampland. So you can also find some reviews and some lectures here. Okay. So the goal of the swampland program is to determine these constraints, okay? So to understand what are the constraints that an effective theory must satisfy to be consistent with quantum gravity at higher energies, okay? So even if the effective theory is defined at a low energy scale, it must satisfy some constraints so that you can guarantee that it will be completed by quantum gravity at higher energies. And this is what this is interesting because these swampland constraints are giving you some UV imprint of quantum gravity. Okay, this is like the hint that there is a quantum gravity description at higher energies. So we have some proposals for these constraints, which are called swampland conjectures. And they are typically motivated by string theory and black hole physics, but we expect them to be more general features of quantum gravity, even beyond string theory. So I will comment a bit on this later on. So I want to say three things. Well, first, this swampland program is like a new field of research that has arisen, and there's a great deal of activity in the past few years. And the reason is that because we always knew that not everything is possible, like there are always some constraints, but we thought that these constraints were not very important. And what has happened in recent years is that we have realized that these quantum gravity constraints are much stronger than what we originally expected and can impose really non-trivial constraints at low energies. Why is that? I can explain in more detail if someone is interested. It's related to the fact that gravity is different than the other interactions. I mean, the reason why it's so difficult, right, like to combine quantum mechanics and gravity is because gravity has some features that make it very different to electromagnetism or the other interactions. And they are correlated to the fact that gravity induces some what is called UV-IR mixing. So there is a correlation between high and low energies. Or if you wish, there is a correlation between long and small distances. And this is something that only is introduced when considering gravity. As I said, I can explain more detail. You can understand it with black hole physics. You can also see many examples in the string theory of this. And it's actually related to these dualities that we were discussing in the previous talk that relate long and small distances. So this is what makes this constraint stronger. Okay, so let me give you a bit of history. So I told you that there is a lot of activity in the past few years. So the point is that the first Swampland conjectures, like the first proposals for universal constraints coming from quantum gravity, were proposed around 2006. But there was not much activity on that. This is like the number of citations per year, until recently, in which the field is exploding, is growing a lot. Okay. So there are many more people coming to the field and having papers and citations and so on. These are three reference, the three original papers for these Swampland constraints. To the extent that if you check in arXiv, where we publish all the papers, which ones are the most cited papers since 2018, these are the 5 most cited papers. The top 4 are actually Swampland papers, are related to the Swampland. So it's really changing the string theory community. Well, the high energy physics. This is all high, not just string theory, but TH is high energy physics. Okay, so why is this? What happened, right? Like, what happened here? Like, there was suddenly this increase in activity, no? Like, so what happened is that there was an experiment in 2014 that triggered this mini revolution here. So what is this experiment? Well, the point is that there was some announcement from BICEP2, which is some cosmological experiment that claimed that had detected primordial gravitational waves. And this announcement went against some of these originally proposed Swampland conjectures. So then people started to check, I mean, I, including myself, we started to check what was going on. Like, there were these old papers that were claiming these universal quantum gravity constraints, but the experiment was against that. So maybe it meant that the conjecture was not correct. Maybe it meant that string theory was not good because this conjecture was very motivated by string theory. So there was a lot of activity there. And then what happened is that the signal turned out to be wrong. So the experiment was not correct, and there were no primordial gravitational waves. So the conjecture was right. And this was very interesting because then, even if we didn't have any experiment to compare with anymore, the impact on the community had already happened. Like, we had realized that these Swampland conjectures are very powerful and can really tell non-trivial things that we can connect with experiments. So in the same way that we had with BICEP, maybe with future experiments, if we understand better the Swampland conjectures and we can prove them or be more confident about them, then we can give predictions that can be tested in future experiments. Is there any question? Should I continue? Okay. Okay, so let me say 3 things about the Swampland program, why at least I find it so exciting, and why it's capturing all this attention. So first of all, it's a shifting attitude in how to progress in high energy physics. Okay, so the traditional view when constructing effective field theories is that you can write, since you don't know what's going to happen at higher energies, no? How to complete the theory. In principle, you just write down a consistent looking effective field theory and expect that will arise from some more fundamental theory at a smaller distance scale, and just try to check it with experiments. Okay, so like typically in effective field theories, you just assume that any effective field theory is fine. Somehow it will be completed if you continue going on in energies. And it's just a matter of checking with experiments to fix the parameters and so on, and find which one is the correct one. This is based on this expectation of separation of scales, that you should be able to construct the theory at low energies without worrying too much about what happens at high energies. But these Swampland constraints are suggesting that this traditional view is not correct, and that not everything goes, so that you cannot just construct any effective field theory. So it's a bit a waste of time just to construct random effective field theories without being sure if they can be completed in the future. So when constructing an effective field theory, you have to make sure that it satisfies this quantum gravity constraint. So it's like new rules that you have to satisfy, so that it can be consistent with quantum gravity at higher energies. And the conclusion then is that the shift in attitude is that people, when constructing models of particle physics or cosmology, are starting to take into account these new constraints, okay, like new rules to satisfy. And that's why I said that at the beginning that quantum gravity matters at low energies. Okay, you cannot just ignore it and assume that somehow your effective field theory will be completed. So this brings interesting phenomenological implications. We can use these new rules, these new constraints, as new guiding principles to construct models in particle physics and cosmology, which is very nice because it provides like a new avenue how to make progress. Even if you don't have an experiment that is telling you how to proceed, sometimes you can already classify what are the possibilities that will be consistent with quantum gravity and reduce the number of models that you could in principle have. So yeah, there are many papers in which we have some constraints on inflation, dark energy, dark photons, and so on, coming from Swampland. And also, I don't have much time to explain this, but you can also ask me if you're interested. They can bring new insights to solve what are called naturalness issues. So the discovery of the Higgs boson or the accelerated expansion of our universe come together with some naturalness issue that we don't understand why the Higgs mass is so small, or why the dark energy, the cosmological constant problem, cosmological constant is so small. They seem to be unnaturally small because you would expect that they are much higher. And that means that there is something at high energy that is making or is explaining why they are so small. And this something could be quantum gravity. Like maybe they seem unnatural, but it's because we think that every value of the parameter is allowed, but that's not true. Not every value of the parameters will be allowed. It's not consistent with quantum gravity. So maybe once you understand very well what values of the parameters are allowed, you realize that the only possibility is that the Higgs mass is small. I don't know, something like that. So it's an opportunity. I mean, the fact that quantum gravity matters is really an opportunity to bring new insights in particle physics and cosmology. And it's nice because some of these Swampland constraints sometimes are not very intuitive from the low energy perspective. So the EFT expectation, effective field theory expectations, fail in the presence of gravity. And we can aim to answer questions like why gravity is so weak, what new particles could we discover, why our universe expands, how stable is it, or one example that I will show you at the end of the talk is why the neutrino mass, so this is the lightest particles that we know of, seems to coincide with the scale of dark energy which describes the acceleration of the universe, which in principle are two completely disconnected things, but they are of the same order. And we have a quantum gravity explanation for this. Okay, so let's go to the third point. So also, I mean, why the Swampland program is receiving so much attention is because within the string theory community, it also provides a change of paradigm. Okay, so the traditional view is that string theory predicts a vast landscape of solutions of universes. And that's because even if it doesn't have free parameters, you can have, since we have extra dimensions to make string theory consistent, we can have many configurations of these extra dimensions and so on. And this gives rise to different ground states, different vacua. and each of them is a different universe. Okay, and this is the landscape, the string theory landscape, okay, of solutions, and is the main reason, one of the main reasons why it's so difficult to get predictions from string theory, because you have many options, and it's difficult to find the exact one that would correspond to our universe. Okay, so this sometimes made people say that then string theory cannot give predictions, everything is possible because there are so many possibilities that probably everything is allowed, and then it's not predictable at all. Now, the point with the Swampland is that, yeah, we have a landscape, there are many different solutions, but the Swampland is even bigger. Like, there are many others that are not allowed, okay? So even if we have many solutions, still we can try to understand what is the difference between which ones belong to the landscape and which ones are in the Swampland. Okay, so there are many other things that string theory cannot reproduce. Okay, there are many universes that would not arise from string theory because they are not consistent with quantum gravity. So the new approach is that instead of trying to identify the concrete string theory solutions that would describe our universe, which is the traditional approach in string phenomenology for the last 50 years, the new approach is that we try to identify what are the universal features that all the universes in the landscape satisfy. Okay, so we don't care about understanding which one is the specific one that we live in, but we want to understand the universal features that we need to satisfy to be consistent with string theory. And these universal features, these universal patterns, can already provide predictions. So this Swampland approach recovers the predictive power of string theory. So string theory is predictive, and we have concrete predictions coming from these universal features, these Swampland constraints for particle physics and cosmology. And yes, this already said, yeah, the Swampland is bringing a new approach. And that's why, like in the recent conferences of string phenomenology, you can find many Swampland talks talking about this, because people, yeah, are excited. No, we all want to connect string theory to the real world. Okay, as a side comment, it's also making progress in this very important question, which is to what extent string theory is unique. So here I was talking about the string theory landscape, no? But is the same that the quantum gravity landscape, or there are more quantum gravity theories that are not related at all to string theory? In other words, can string theory reproduce any effective field theory that is consistent with quantum gravity? Because if it can reproduce any effective field theory that is consistent with quantum gravity, then even if there are other possible descriptions that could do the same, we could just focus on string theory, like somehow everything would be connected to string theory. So this is a very important question that, of course, we don't know the answer. There are alternatives to string theory. We don't know if eventually they will be connected. It could happen. But it's interesting, and I find very amazing that with this Swampland program, where we have a new handle, like a new way to approach this question. Because if we can really identify universal features of quantum gravity, then we can try to test if string theory can reproduce everything that would be consistent with those universal features. And there are many works in recent years that are addressing this question in higher dimensions. So it's difficult. Still, we don't have an answer in 4 dimensions, like for our universe. But you can, as a theoretical exercise, you can do it in higher dimensions where everything becomes easier. And it's already the case that have been proven that for dimensions bigger than 6 and supersymmetric theory, so here you need to add supersymmetry to be able to answer this question in these works, then it has been shown that string theory reproduces everything that seems to be consistent with the quantum gravity constraints. So it points towards universality of string theory in these higher supersymmetric theories. And of course, the goal for the future is try to go down in dimension and get rid of supersymmetry, but that's technically harder. Okay, so what is the Swampland methodology? So how we work in the Swampland program is that we identify some pattern we identify some universal feature that we think should be satisfied, typically motivated by thinking of black holes, or like unitarity of black hole evaporation, or thinking of string theory, and so on. And if we have some arguments in favor of it, we have some Swampland conjecture, and then we have to work harder to try to prove it. So we, as I said, at least we know that string theory is a consistent theory of quantum gravity, so we can use it as a test in laboratory. And most of the work is trying to find quantitative evidence in string theory for this conjecture and prove it in different setups and so on, using the geometry and the topology of the string compactification, so using mathematical proofs. So this is one corner that people work on. But of course, then this cannot be the only thing, because if we want to understand general features of quantum gravity, we need to understand if this pattern, this Swampland conjecture, is more general beyond string theory. So then you also need to find other arguments, like based on black holes or holography, unitarity, causality. So you need to understand, even if it's in this context, it's more difficult to have a quantitative proof, mathematical proof, you can at least give heuristic arguments of what would go wrong in general if you don't satisfy this Swampland conjecture. And only if you combine both things, then we start thinking that this Swampland conjecture is a universal feature of quantum gravity. Okay, so if we have the quantitative evidence from string theory, but also arguments beyond string theory. And then, of course, there is another branch of the Swampland program, which is focused on studying, like assuming that the conjectures are true and studying what are the phenomenological implications for our universe. Okay, so I put here some map, like a network of the different Swampland conjectures. So everything now is very abstract. I'm just telling you that there are some Swampland constraints, but I didn't give you a single example of what these constraints are. So what I'm going to do in the rest of the talk is to explain just two of these constraints, just two examples, and what could be the implications. Okay. Any question before I go on? Okay, I guess you can just ask at the end. Okay, so these are the proposals for some Swampland conjectures that we have. As I said, motivated by string theory, black hole physics, and so on. And it's still work this is still under construction, right? It's ongoing work, because depending for which one, we have more or less evidence, or maybe for some of them, we already have some proofs in string theory. For the others, we have arguments beyond string theory. For the others, we don't have either one or the other one. So it depends on which one. The level of evidence is different, okay? But what I wanted to point out with this slide is that something very interesting that is happening in the past couple of years is that we are realizing that all these conjectures seem to be connected to each other, okay? So even if they were formulated as independent criteria, there seem to be more and more relations between them, which hints that they might be just different phases of the same underlying quantum gravity principles that we are starting to discover. And this provides consistency and a more solid ground for these conjectures, right? Because if you have different ideas, but then they seem to be connected, then the whole picture starts making more sense, right? Like it's like a global robustness or consistency. So it's I find very interesting to understand better all these relations and try to reduce all these conjectures to the minimal set of statements that would reproduce everything. Okay, so let's come back to the map. And now, as I promised, let's study two of these examples, okay? So I put in purple the ones that are the most important ones, which are no global symmetries with gravity conjecture and distance conjecture. I'm going to discuss a little bit no global symmetries and the weak gravity conjecture. Okay, so no global symmetries. So what does this mean? So let me just give you some intuition. So we love to work with symmetries in physics. These are quantities that are invariant, that do not change in time. So when doing some physical phenomena. And this helps us a lot to provide some description of what's going on. Now, there are different types of symmetries. Here I put just 3 examples, like rotational symmetry, like I can rotate the picture, it doesn't change. Electric charge, like the electric charge is conserved in a process. Angular momentum, and so on. The point is that some of these symmetries are not allowed in quantum gravity. Like for instance, the rotational symmetry would be one symmetry that should be broken at higher energies. So let me explain the intuition, so why this is the case. So, well, the formulation of the conjecture is that some kind of symmetries, which are known as global symmetries, cannot be exact in quantum gravity. So quantum gravitational effects should break them. This is the oldest statement of quantum gravity, like even before thinking of string theory. This is a general feature that we think is general, like it's universal in quantum gravity, but has been proven more recently in the context of string theory. And the intuition why this is the case is related to black hole physics. So in order to explain this, let me try to give you an intuition of how to understand what is a global symmetry, how to distinguish what symmetries are good or bad in quantum gravity. Okay, so in order to understand if the symmetry should be broken in quantum gravity or not, you have to ask yourself the following question, which is, can we measure the conserved charge from very far away? So here I have like these 3 types of symmetries, and the question is, can I detect this conserved quantity, this invariant quantity, even if I am not there? If the answer is yes, then this is actually a gauged symmetry. If the answer is no, it's a global symmetry. And these ones, the ones that we cannot measure from very far away, are the ones that should be broken in quantum gravity. Okay. So for instance, an electric charge, you can measure it from far away because of the gauge field, like you can carry the information far away. But the rotational symmetry, I cannot measure this unless I see it with my own eyes, like you can detect it. So there's nothing carrying the information far away. Okay, so why is this? So why, if I cannot measure it from far away, is a problem with quantum gravity? Okay, so let me give you some intuition based on black hole physics. So black holes are very exciting and mysterious solutions of Einstein gravity, general relativity. There is something that is very fundamental about the black holes, which is the fact that they behave as thermodynamic objects. So they seem to have a finite entropy. And this entropy, you can think of it as how many different ways could lead to the same black hole. So how many, it's like the microstate. So how many different ways you could construct the same solution. Okay, this is like a measure of the entropy of the solution. Now, imagine that I have some particles that are charged under a symmetry, and I throw the particles into the black hole. So I construct different black holes with different values of the charge, of this global charge. Since global symmetries cannot be detected from far away, it seems that I could construct infinitely many black holes with different values of the global charge, like I can throw different numbers. Imagine that the charge is how many particles I throw in, like the baryon particles, like this is a baryon symmetry. So by throwing different values of the number of particles, I will have a different value of the charge. But see, the global charge cannot be detected from very far away. So there is no way to detect that this is a different black hole when you let it evaporate. So this would give rise to infinitely many black holes with different values of the global charge that look the same from far away, and this gives rise to an infinite entropy. And this is a contradiction because black holes have a finite entropy, finite temperature, and this global symmetry will violate these entropy bounds. Okay, this is, I don't know if it's too simple or too technical for many people. I just wanted to give at least one intuition for one of these Swampland constraints. But the take-home message is that there's global symmetries which are very typical in effective field theories. We all the time have symmetries when constructing models, but still quantum gravity is telling me that these global symmetries at high energies must be broken at some point. And this is something which is not intuitive at all if you don't consider gravity. Okay, so it's a constraint that can have implications and that we believe is universal. Now, what I gave you is just some heuristic motivation based on black holes, but why we are confident about this constraint is because we have more quantitative proofs in string theory and also in IDS-CFT in holography. And also, we can see that it's correlated to unitary black hole evaporation. So, yeah, and topology changing processes. So, if someone is interested, you can ask me more about it. The message is that in order to have a global symmetry, you can believe me that you will need to have a fixed topology of space-time. And this is something that is broken in quantum gravity. Like topology changes. Okay.
Sorry, Irene, can I ask a question?
Yes.
It's just some sort of clarification about these global symmetries. Jay, you can hear me, right?
Yes, I can hear you.
So when you're talking about the electric charge, so normally if you don't have point charges, you have a one form U1 electric symmetry.
Mm-hmm.
Yes. And that's a global symmetry.
Yes.
Yes. And then you put in point charges, you break that symmetry.
Yes.
Violates that symmetry, so that global symmetry is gone. But you have an emergent global symmetry that counts the number of point charges, which is the thing that you use to compute the electric charge. But somehow you're not excluding that. You're not counting that as a global symmetry. Is that because it's emergent?
Yeah. So
fundamental symmetries versus it's just a clarification.
Yeah, when you say emergent, you meant that. I think. Let me see if I heard well the question. So you mean that even if it's not a full symmetry of the theory, it emerges at low energies. It's an approximate symmetry, right? Like if you go below the mass of the particles, it seems you don't have particles, and you recover some emergent one-form global symmetry in that case, right? That's completely fine, because the whole point is just that they cannot be exact symmetries of the full theory. So they must be broken at some high energy scale. But as long as they are broken at some high energy scale, for quantum gravity is fine. Okay. So that's fine. I like that you mentioned this example because, yeah, this is one example is you could say, okay, it's nice, like one form global symmetry is predicting the existence of particles of charged states to break the symmetries. But this statement by itself is not telling me what is the mass of the particle, right? Like how much I have to break the symmetries, which would be even more interesting. And this is what is quantified by other Swampland conjectures. So yeah, indeed, emergent symmetries, like approximate symmetries, are completely fine from this perspective. But you can now go to a more refined question and ask, okay, exact global symmetries are not allowed in quantum gravity. They must be broken at some high energy scale. At what scale? How much do I have to break the symmetry? Can I quantify this? And yes, you can. You can do it. And this is what is done by the weak gravity conjecture, for example. So I will explain this later in one slide. Okay, thank you. Okay. So yeah, just before going to this weak gravity conjecture, let me just point one thing. So, okay, I said no global symmetry. So let me give you one example of one global symmetry that we know in particle physics that therefore cannot be exact. according to quantum gravity. If you take the standard model of particle physics and you consider, for instance, this decay process from to the proton and electron neutrino, there are two conserved charges that occur in the process of decaying. One is what is called B minus L, which is the number of baryons minus leptons. This is a global symmetry. And the other one is the electric charge, which is a gauged symmetry. The first one is the one that cannot be exact in quantum gravity because it's global. There is no way to carry the information of how many baryons or leptons you have very far away, okay? Unlike the electric charge. So there are two possible solutions. One of them, I mean, even if this seems to be like an emergent symmetry in standard model of particle physics, there are two options. Either the symmetry is actually exact, really exact, but because it's gauged, not global, and that means that there should be a new force, a new gauge field that is associated to this symmetry to make it gauged. So it's a new interaction, so you would predict a new interaction in nature. Or the symmetry must be broken at some high energy scale, which, for example, it would imply that the proton cannot be stable. Okay. Now, what would be interesting, as what I said before, is to quantify like how much it has to be broken to understand what is the lifetime of the proton, or what is the new force, like how weakly coupled is it. And this is all correlated to understanding how much we have to break the symmetries. So this is what is quantified by the other conjectures that I have in this network, in this map. And just to give one example, let me then discuss the weak gravity conjecture, which quantifies, in a sense, how much we have to break some of these symmetries. Okay, so this, I will be quick because I don't want to spend a lot of time. I mean, you can ask me later in the question, so I will just tell you briefly what the conjecture is and some of the implications. And then I will go to the conclusions, and then people can ask more questions in general. Okay, so the weak gravity conjecture says that gravity should be the weakest force. Okay. Which means that there should be a particle, some state, in which gravity acts weaker than electromagnetism, than the gauge forces. In practice, in the equations, that means that the charge of the particle has to be bigger than the mass, because the mass is what determines how weakly or strongly couples to gravity, and the charge is to the gauge charge. So it must couple, like gravity must be weaker, so the mass must be smaller than the charge. Okay. Now, I didn't put here the motivation. I have it in backup slides. You can also motivate this using black hole physics, because otherwise you would have stable black holes, and that would also violate entropy bounds and so on. And you can also motivate it from breaking global symmetries. That I also removed it because I thought it was going to be too technical, but now I regret it. But the point is that if the charge is very small, the charge depends on the value of the gauge coupling for the people for the physicists. So if the charge would be too small, you would have a coupling which is very small. And if the coupling goes to zero, you would restore a global symmetry. So having very small charges are like having approximate global symmetries. So if you want to quantify how much you have to, how approximate the symmetries can be, you can try to put a bound on how big the charges must be. And that's what the weak gravity conjecture does. Okay, so of course the conjecture is satisfied in our universe. The electron itself satisfies this. The mass is much smaller than the charge in Planck units. But the point is that this is not just random. It should have a quantum gravity explanation, and it becomes non-trivial when applied to new interactions that could appear beyond standard models of particle physics, like in the future. So this is hinting that hidden forces, if we have new forces in nature that we didn't detect yet because they are very weakly coupled, they are problematic, because if they are too weakly coupled, if these charges are too small, they could violate this weak gravity conjecture. So they are disfavoring quantum gravity unless they come together with many new light particles. And I say many because we actually can show that it's not only one particle that must satisfy this, but infinitely many. So this is another example in which EFT expectations fail, in the sense that typically it's completely fine to have weakly coupled interactions. These are like the classical descriptions. Everything weakly coupled is nice. We know how to compute things. But quantum gravity is telling you that, hey, weakly coupled means that you are too close to restore a global symmetry. Global symmetries are not allowed in quantum gravity. So this is problematic. Something new must happen. You must have new light states, and you predict new physics from that. Okay, so just to finish the talk, you can use this to provide some correlations between masses and charges and other quantities in our universe. So for instance, I started my talk talking about these two frontiers in the knowledge of physics, in particle physics and cosmology, at small scales or large scales. At small scales, one of the mysteries that we have in particle physics is the mass of the neutrinos. So these are the lightest particles that we know of that have been detected experimentally. And we just have an upper bound on the mass. We don't know exactly what the absolute value of the mass is. But we know that they have some mass that has to be very light. It's much lighter than any of the other particles. So how to give rise to this mass and so on is one of the puzzles in particle physics. This is on one hand. On the other hand, in cosmology, one of the very big puzzles and most important and open questions is what is the dark energy, right? Like what describes the accelerated expansion of our universe. And it's funny that the scale of this dark energy that is measured experimentally, when I put it in Planck units, is of the same order. This 10 to the minus 11 electron volts is the same order that this upper bound for the neutrino mass is. So this might just be a coincidence. I don't know, we have this correlation, two things that have nothing to do, like neutrinos and accelerated expansion of the universe. Might be a coincidence, but we could show, for instance, forgot to put the reference, but we saw that some generalizations of this weak gravity conjecture that relate the mass and the charges and so on can be used to show that a universe consistent with quantum gravity must have particles, in particular fermions, like neutrinos, that are lighter than the value of the dark energy, of the vacuum energy. So this is precisely what we are observing, and it could be that indeed has a quantum gravity explanation. So you are relating to things that a priori were disconnected and that you cannot explain unless you take into account quantum gravity. Okay, so let me conclude. So the message I try to convey is that consistency with quantum gravity can have important implications for our universe that we are only starting now to discover. So we are starting to put bounds and constraints on particles or the evolution of the universe and so on. And everything is based on the message that not every effective field theory is consistent with quantum gravity, unless it satisfies some additional constraints. So this is motivated by string theory because it mixes long and small distances and so on. But we are working and we are trying to understand how general it is, and we think it's much more general than string theory. It's like a general feature of quantum gravity. And this is what the Swampland program is about, to understand these general features. So these Swampland conjectures can provide new guiding principles to progress in high energy physics. It's a very ambitious program because it's difficult to be universal in the context of quantum gravity, but the potential outcome is so big that is what is making all of us excited. So thank you for your attention.